Okay, I'm going to start. So we're finally at the point where we can do some generative security applications. And we're only in week 7, but you know, there's no other way. I used to start this earlier, but there's just too much other stuff to do. So you have all the tools you need to very quickly develop applications, generative security applications. You know how to, write programs to apply models. So LLM applications, you know how to secure them, and now you know how to vibe code as well. So you got all the superpowers, and now we're just going to point those superpowers to just all the different things in the security space, and then maybe you can solve some useful problems. So that's where we're going today. You started with generative AI models, then you started building generative AI applications, and then you learned about security issues with generative applications, and now you know a lot of you prompted your coding agent with security parameters that warmed the cackles of my heart to see the prompts there and be like, yeah, at least I'm sending people out in the world that's not going to produce total garbage. There's some security measures being built in, so that makes me happy that I saw that in your prompts. And then you did code generation with the agents, and then command and configuration generation last class. And they're kind of security related-ish, but they're not actually security applications. So now we're going to get to more traditional security applications. And so that was the whole point of the course. I actually had this up in like the first lecture, and then you could be like looking at this and like, well, where the heck was all of that? Well, all of that is basically going to be smushed into the last 3 weeks of this class. And that's what we're going to start. Okay, so the rest of this course is a very brief tour of some of the things that they are looking for LLMs to automate. And I mostly focused on offensive things and maybe a little bit of vulnerability remediation. But I don't, there's a little bit of threat intelligence and log analysis as well. So it's a mixture. But we're going to today do the top 2, code documentation, code summarization, and code classification, as well as reverse engineering and deobfuscation of code. And these things are often towards the end of identifying malicious software or malicious behavior, and then flagging it. So that's kind of what we're looking at this week. Next week, we're going to do automated vulnerability discovery and automated exploitation. And then the last week, we're going to do some defensive things, threat intelligence and log analysis. And then we're going to also do social engineering and phishing, which is, from an attacker standpoint, this is the heaviest use of LLMs, is to do the social engineering and make that better. Okay, one of the things I like to show people, and you probably, because of a lot of you are wrestling with models and realize how fragile all this stuff is, just to be mindful of overconfidence. So basically a year ago, the CISO of Claude posted this, where they're like, hey, this is groundbreaking. Claude 3 Opus is capable of automatically discovering zero-day vulnerabilities in the Linux kernel. And he posted this, and he was like, oh, here's the demo. This is what it found. This is the file. This is the replay of the session. This is Opus, the prompt that Opus was given to be a Linux kernel engineer. And then this is the response that Claude gave. So sounds really good. And then someone who actually knows about what that code is in that file was like, that actually doesn't look good. This doesn't seem to be the right thing. And the CISO was giving the actual response almost like an LLM. Like, this is what the LLM would give you. Oh, okay, you're right, of course. And then the follow-up was like, no, this is actually incorrect. And then the CISO had to backtrack. They're like, oh, it looks so good that I believed it to be true. And this is what you will come across when you try and build your application. Something will look really good, but it'll actually be garbage. And I did find this in some of your screencasts. Like, I mean, most of you, because it wasn't required in the screencast, most of you didn't look into the code that got generated in your vibe coded app to see whether or not it was actually correct. And I did come across some snippets and I was like, oh, that's completely incorrect. That's something that, you know, I had hoped to like get you more practice with, like showing you where the thing is wrong. But hopefully when you do this week's lab exercises, I'm giving you the ground truth. I'm forcing you to look at it, and then hopefully the LLM will either validate your confidence or really give you the reasonable picture where it's going to give you a lot of incorrect results that look pretty good. Not a lot, but it's going to give you incorrect results and make it look good. And this is something that you really cognitively have to be aware of so you don't buy all of this stuff like the CISO did. Okay, so so I looked at this up. I'm like, why do we believe all this stuff? It's psychology, actually. And it's basically what I mentioned in the very first week. It's this survivorship bias and achievement bias. We're always focusing on the illusions of understanding and the illusions of belief. And because we got the positive feedback, we'll always believe it. So generative AI is regularly given credit for plausible looking but fatally flawed outputs. And because we're not equipped to doubt it, because it's so confident in its BS, we can't call it out. And so hopefully you're getting better at calling out the BS of the model as part of this course. So it is actually a cognitive limitation. This is why I saw this article. I'm like, oh yeah, this is happening to everybody in the AI space because we're actually vulnerable to this. All of us are. Okay, so that leads us to just a couple days ago. Anthropic's Claude Code Security, 500 plus zero-day vulnerabilities. 500 high severity ones. And like, do we believe this? And then we have just last fall, OpenAI Aardvark was like 92% of known and synthetically introduced vulnerabilities in test repositories. Should we believe that? And so I'm like, I don't know, actually. The answer is I don't know. But we are in this, not in this particular class, but next class, we're going to look at vulnerability detection and discovery. Okay, so for this class, we're going to do code documentation and summarization. So the types of tasks we're going to look at, and this is not really that security related, but I just put it here because it's summarization. We're going to look at automated documentation generation. We're going to look at code summarization. We're going to have the LLM describe the overall purpose of the code it sees. We're going to have it sort of look at large code base. Actually, maybe not the second one. That was the previous week. And then we're going to try and have it identify particular behaviors in code that it's been given to see if whether or not it can identify potential malware. And then we're also going to do this classification sort of benchmark where we're going to have a bunch of code and we're going to ask the LLM to determine whether it's malicious code or benign code, whether it's obfuscated or not obfuscated, whether or not it's performing a data exfiltration operation in its code, whether or not it's trying to persist in the machine that it is being sort of executed on. And these are all super helpful signals to determine whether or not the thing is, you want to run the thing or not. And so these are, you know, if you have a filter and you're trying to determine whether or not a piece of software should run on your machine, these are nice things to have. If you get an LLM to accurately do this, then you have a level of protection. And this is what people are actually doing, especially if you have local inferencing on your machine and you can do some simple things like this. You'd be like, oh, I don't need antivirus. Forget Symantec, they're terrible. They make my computer super slow. I'll just have an LLM figure it out. So that's where like security stocks just took a big hit. Actually, no, IBM took a big hit. Some of the security stocks also took a big hit because Claude is saying that we could actually use the model to do these, subsume some of these operations that have been traditionally sort of implemented by the vendor, by like McAfee, by Symantec, by all these antivirus companies. So that's a good, an interesting thing to think about. Okay, so we're going to start with documentation generation. This is a thing, CodeWiki, and it's like never comment your code ever again. And so like, okay, like how well does this work? So this is CodeWiki. You just attach it to your repository and then you're done. And so I give you an exercise so you can kick the wheels on this. It's super good at this. You're like, here's my code. Here is the kind of comment or documentation I want you to produce. So you have to actually know about how documentation is being, the standards that are being used to produce documentation. And so there's the Sphinx standard, there's Google style doc strings, and it basically is a particular format of your documentation. And it's typically the comments right after the function definition. And this is parsed by other tools to generate those website documentations, PyDoc. And so if you don't, as a developer, you want to write the code, but you don't want to write the doc string, see whether or not an LLM can do this, and it definitely can. So this is a no-brainer, but I just want you to see it. But you have to know exactly what kind of docstring formats there are. The other one is NumPy docstrings. It's a different kind of sort of syntax, but it's the same idea. So we shouldn't be doing this manually anymore, and that's what the point of this exercise is. Something that's more security related is code summarization. So not only is code summarization useful for if you're doing your own development for benign code, but typically if you want to identify and detect unknown code as being malicious or not, you want some way of doing a pre-filter. You can't look at all the code going across your desk, because there's too much going flying by. But what you want to do is have the LLM pull out the ones that it thinks are suspicious, and then you would look at those. And so, how well can the LLM summarize what code does? So here's an example. Take a look at this Python code. What do you think this thing is doing? Anyone? Just throw it out there. Stealing the clipboard. Close. Yeah. It's putting something into it. It's not defined yet, but here's a comment. It's like text found in the clipboard. I'm going to pull it out. Target clipboard is equal to clipboard. Here's another one. This check is undefined, but what you're going to, what this output, like the code for the check doesn't appear, but this logging message is like, oh, this is probably an address. Like, what kind of address? And why would you want to set a clipboard to something different? So yeah, and this is the rest of it. No, this is a wallet address. So this is malware, and I think this showed up in a Python package. What it is that you run this Python program, and in the background, it's sitting there looking at the clipboard, and when you're about to do a Bitcoin transaction, you're not going to type your Bitcoin address completely manually because you might make a typo. So what you're going to do is you're going to copy and paste it into, from your wallet into the web UI that's going to do the transaction. And then the adversary is like, this looks like an address. I'm going to replace it with my own wallet. And then if you aren't checking, they get your Bitcoin. So then you're like, yeah, that's probably malware. So, this is an example. I think this is one of the examples I have you analyze in your lab. I'll give you some other ones. Here's another piece of code. So this is ground truth. So when you do the lab, you should be able to say, okay, the LLM is super accurate or not. So what is this thing doing? I didn't give you the function name because that would give it away. What do you think it's doing? What's going to be in this file at the end of f.close? What are the contents of this file? What's it? So you're going to do a recursive walk in the operating system. So this does actually, I don't know if you've ever used OS walk. It's going to walk the directory tree from slash. It's going to get the root directory, the subdirectories, and all the files in there. Yeah, it's going to write all of the different files that it finds to a file that match a particular extension. So yeah. It's like a ransomware list. Yeah. In fact, this is where these snippets, so some of these snippets came from these kinds of malicious software. So this is similar to what we just had you, like, that was part of your lab. You vibe coded the ransomware thing. Like I was doing the find PDFs. This is just doing all the extensions and trying to enumerate all of them. And then later on, you'll open this file and then you'll read and encrypt and do all this other stuff, or exfiltrate. So it could be a data stealer. Okay, here's another interesting one. And again, this actually is one of the code snippets that you'll send to an LLM and get its opinion. I just want you to see this because all this stuff is now, like, they're going to integrate the LLMs in all of these different functions. And so you'll see why. It's like, well, can I depend on this? So what is this thing? What might this thing be doing? It's a little more self-evident. It's running on a target victim. Any of you program sockets directly? You know, I think that's probably it. Yeah, this is Berkeley sockets. So this is a, basically on the victim, it's got a socket that's open, receiving commands from a bot master. And then when it receives a command, it's like the server sent me a command to execute. And if it matches exit sysinfo, or no, either exit or sysinfo, exit will basically terminate the sort of the implant. And then if it's sysinfo, I basically get the system's information and I send it back to the destination. So that's basically, I receive this command and then I send the result of executing the command that the server sent me. So this is a remote access sort of Trojan where the server is sending the compromised machine commands for the client to respond to. Okay, yeah. Yeah, you could. So there are so many different ways of writing Python malware, and we'll get to the more devious ones. But this is the kind of stuff to look for. And we're going to actually, as part of your lab, you're going to track to see when a Git repo gets one of these things in it. It'll be like, should I accept this as a pull request? Probably not. And this is where the automation and the workflows, you're like, yeah, maybe I should have an LLM. Because, you know, usually like manually, like the developer of the GitHub repository is getting all these pull requests and they're manually vetting the thing. And if you got a ton of these things, like curl got so many of these things, they're like, we're going to ignore all of them from now on. If you don't have the bandwidth to look at all of them, then maybe you do want the LLM. Or I mean, so this is why GitHub is rolling in all of the AI features into their like actions and their pipelines. Because it's like this kind of stuff, yeah, you might be able to automate that. And it might be useful to some repositories if this is automated, where they can be like, this doesn't look kosher, I'm going to stop. Because this is what's happening in a lot of repositories. Okay, here's another one. This is an interesting one. I don't want you to read this one, but basically it's doing something similar. It's going into a particular directory in the file system. And if it finds something in that file system, it will basically open up a file, that file, and post it to a Discord webhook URL in its entirety. So basically, it's using Discord servers as a command and control to basically do data exfiltration from the client. And so this is something, yeah, this is definitely bad. Like, can the LLM describe this to you? And it's got good error checking too. So the malware is actually checking for errors. And it's also trying to stay under the radar. So it's trying to make sure that it doesn't show up on sort of detectors because, you know, it's the frequency of the data uploads that these tools are trying to use to detect attacks like this. So if you look, it's upload files in the directory. It basically goes through every single file and then tries to upload it to this webhook, which is on a Discord server. Okay, here's another interesting one. This is where, so in this particular code example, they get the webhook, the exfiltration URL from this URL. So they download this and then they get the destination of the upload, and then they go through, and this is basically, the Steam platform for video games. It goes into the Steam directory and it finds the session information. It finds all the Steam sort of the files in the Steam sort of directory, all the important messages, and it basically zips it all up and then sends it to the hook. So you see this request.post to that hook. Okay, so this is something that I can explain. Like, we can read it as humans and understand it. And then the idea is the LLM going to accurately depict the same operation? And, it was hit or miss before, but I think it's probably going to be a hit this time around. Here's another one. So if you haven't taken the malware reverse engineering class, this is the way that malware tries to see if an analyst is trying to reverse engineer it. So typically, if you have a piece of malware, you put it up in a debugger and you step through it. And most malware is going to be like, well, if I'm running in a debugger, either on Windows, because is debugger present is on, or on Linux, because when GDB uses the ptrace interface to attach to the process, then you can check for those things and you can exit. Both of these will exit. So I'll stop the execution. And then if not, I will pop up a reverse shell. So this is basically an debugging remote access Trojan in this case. And the LLM should be able to at least give you that. Okay, so the next set of exercise, so you're going to do these on the code samples that are in the repository. You're going to read the code sample. You're going to, sort of understand it from your knowledge of Python, and then you're going to see if the LLM has the same understanding of it, is the exercise. And I just wanted to go through these examples before you go and do that. Okay, the next one is simple code classification. So here's a prompt. You give it to the LLM. You just say, you're an advanced security analyst. Determine whether or not the code that you see is doing data exfiltration, file creation, process launching, and environmental variable access, because these are all kinds of operations that malware will do. And then moreover, in terms of output, put your output in JSON and do it using this template. So you give it a JSON schema and you say detected true or false for every attribute. So every classification attribute that you're giving it. And then you give it a confidence score, like how confident are you in your classification? And then give some evidence of what supports your classification, and then give me the snippet of code. So you're going to point this to that code that you had in the previous, the summarization exercises, and then you're going to see like how well does it classify code that's malicious or not. It should be pretty easy. Like if you have an os.open, like in Python, you're like, yeah, that's probably, and it's got the right flag on. That probably means yes. But what happens if I obfuscate that? Can the LLM deobfuscate the OS right and the OS open? That's what you're going to find out, because that's an interesting way of trying to evade LLM access. Okay, so then the next set of exercises is a Git repository analysis, and you're going to analyze the course repository, because I know there's ground truth there. But you could use this in your homeworks or whatever you want to develop for this week. You can point it to arbitrary repositories, and you can build out all the different functions that you want to sort of implement with the Git repository analysis. And so I put this in here because the new battleground for malware is GitHub. And so there's all sorts of operations to try and trick developers into basically ingesting malicious code into their repo. So one of the ones that I'm showing here is, so there is this Dependabot service where it goes and it finds vulnerable parts of your code and then automatically produces a patch to fix it. And so it's a useful service, but because it's a useful service and people are using it, attackers are going to spoof this in order to get their malicious code into it. And so then you're like, well, I need to be able to analyze the git commits and the pull requests and the file history to figure out if I've ingested malicious code into my code base. So that's what we're doing. We are going to have 3 tools, and this is just basically, very sort of cursory tools just to give you an idea. So here's one, Git file history analysis. So there's the GitHub package in Python. You import it, you point it to a repository, and you can pull out file information. So you give it a file path, and it'll give you the file contents, the commit data associated with that file, and then the last commit. So that's basically what you're going to provide as context. This is basically a RAG application. You give it this prompt, you provide the context to say, I want you to analyze this file's last commit and tell me what it did. And was it malicious? So that's one of the exercises. Here's another one. I have a particular commit. Like somebody, some developer did this huge commit, and I want you to just go through the commit and make sure there was nothing malicious that was slid in there. So if the developer's account got compromised and you see that they did a commit, you're like, well, let me see whether or not that was the adversary trying to slide in a backdoor or some sneaky malicious code. And then you would be like, okay, well, for that particular commit ID, who's the author? When was it? When did it happen? What was the commit message? And then give me the file changes. And then tell me what it does. Tell me whether or not the code is compatible with the message. Like, did the commit message try and deceive me? That's a red flag. And then whether or not it's malicious or not. And this is something that you might put into your CI/CD pipe, like in your GitHub action. You'd be like, I'm gonna classify these things. Here's another one. You get a pull request from an unknown person, and then it's given a title, description, and the source code diff. And then you have the LLM say, is this legit or not? So you'll see in the course repository, there's a pull request 21 or something like that. And you're like, was this a reasonable pull request, or did it add a whole bunch of malicious code? And of course, because I want this thing to actually detect malicious code, you'll see that there's a whole bunch of malicious code in the diff in the pull request I have you look at, and then you can see the usefulness of this, because an adversary might be like, for a popular project, they're getting pull requests all over the place. And so like, can you sneak in a malicious commit without the LLM noticing it? And this is where you could actually put some social engineering into your code if you know the LLM is trying to vet your pull request to see whether or not it's malicious or not. So that's also an exercise that I'm going to have you do. Okay, so that's the code documentation, summarization, and classification. The next half of the labs focus more on deobfuscation and reverse engineering unknown code. So the first kind of task that you're going to be doing is to deobfuscate code. Malware is often encoded or obfuscated to prevent people from understanding what it does. And so you're going to see whether or not the LLM is good at just simple replacement tasks where they've just renamed all their symbols. And then you can basically do the reverse. You could also come up with malware that is using things like random encodings and light encryption on all of the symbols in its payload, and then doing a decryption operation before running. You can have the LLM automate the decryption and the decoding process as part of your analysis. So that's what you'll be doing. The other thing you can do is to analyze malware functionality after you've done the deobfuscation. So then you'll see these are the operations a particular piece of code does. So that's part of the lab as well. One of the things that you'll find is that because you have a limited context window in some of these LLMs, you might need to do basically what we were doing with the RAG application. You might need to basically do it in chunks, or to target the exact piece of code that you want to get the summary for, the malware summary for. Okay, so we'll start with deobfuscation. So this is the example that you're going to do in the lab. So data decoding and decrypting. So malware is typically using lightweight encoding and encryption only to bypass sort of simple filters. So there's all sorts of filtering going on, and if it looks like you have strings in your malware that match naughty strings that shouldn't be allowed, they'll get rid of it. And so almost all the time, the malware is basically changing the names. So the one that we're going to have you look at in the labs is this OS 10 fairy tale malware. It basically does two things. It XORs the payload with a constant byte, hex 30. And then it just base64 encodes the result and then sends it over. It's put as part of the payload of the malware. So then it also comes with decryption code. And this is the decryption code. It basically loads up that string after the base64 encode, and then it loads up the key for the XOR, and then later on it runs the XOR loop to decode it. It does the base64 decode, and then it runs the XOR loop to generate the sort of the original. So what I'm going to have you do is with an LLM, you could just give it these strings and see if it can figure out that it is XOR. So it is easily base64. So it automatically knows to try base64 decode something that looks like this. But then, like, will it do the cryptanalysis to try and figure out that, oh yeah, if I do what's like a brute force search on the XOR bytes, can I actually get the hex 30 and then decrypt that? That would be awesome if the LLM could actually figure that out. But if it can, then basically the rest of the steps it will also be able to do. But then the next step would be, okay, these are base64 encoded strings, and it looks like it's XOR encrypted with hex 30, or XOR encrypted, and then see if it can do the job. And then you can say it's XOR encrypted with a byte hex 30, and then see if it can do the job. And then if it can't do any of those, and it says then you can actually tell it, give me the code to XOR decrypt using hex 30, and then do the base64 decode. And it should definitely be able to do that. So there's just different levels at which you can ask the LLM to do the deobfuscation and decryption of strings. If you want, for your homework, you could have tools that try all of these things, right? Like you could have like an agent sort of look at these as individual tools. So I actually am not quite sure whether or not ChatGPT or Gemini have built-in tools to do any of this cryptanalysis, but eventually that cryptanalysis should be done as tools in an agent. It's coming. If it's not already, I don't know what the state of the art is, but it would be really cool if you just copy and pasted this string in there and it figured it out itself. That would be surprising. I think it's more likely that once you tell it it's XOR, that it might find the hex 30 and then do the decryption automatically. Okay, so these are the different ways. I'm going to have you sort of interact with the LLM and give it different levels of hints, and then just see what is it capable of doing. And I don't know the answer to that. That's why I figure I'd have you all try and see. Okay, here's some other deobfuscation tasks I'm going to have you look at. So here's an example, a sneaky instantiation of a Python built-in function. What built-in function is it trying to invoke? Just from the method names. It's taking this name and it's saying, oh, this is a pointer to the built-in. So built-ins is a sort of an array, which can basically all of the Python built-in commands are indexed in it. But you don't want to say which function you actually want. You are going to give it some garbled thing, and you're going to say, I'm going to rotate 13 these characters. So the LLM can't say that I'm using that function call. Because if the LLM sees it, it might say that I am trying to create a file. So this is the open, this is the file call. So this is a way of obfuscating code to try and evade detection as being something that will open a file called test.txt and then write to it. So that's the idea. Here's another one. This is the sneaky invocation of what function? So if you look at this, it's basically taking the the ASCII code in decimal and giving you the actual character that corresponds to this. And then you're going to join this entire string, and then you're going to call exec on it. You're going to say exec this Python code. So it's basically generating the string to the Python program to execute. And this is the pattern that you will see malware use. It's not going to give you the actual code that it runs. It's going to unpack it. So this is what we call packing in the malware course. It's like you pack the malware into a representation that confuses the heck out of the analyst. And this is going to confuse the heck out of the analyst. Well, I don't know what code that is. That's actually a print statement. Just when you get to this section, and hopefully the LLM, if the LLM has got these tools, it might actually execute this and evaluate this and then give you, yes, this is a print statement. But you're going to have to test this, because before you can rely on an LLM to do this operation, you have to see if it can. And that's what this exercise is doing. Here's another one. Can the LLM figure out what URL I'm trying to retrieve here? So this is Python requests, and I'm just going to evaluate request.get with whatever is here. So you're like, oh, this is hex encoding. And so the string can be hex encoded. We typically like to write out our strings, but if you want to, if you have a simple string matching sort of filter on your malicious URLs, like some people do, this is going to bypass that. And this is why having an LLM helps you. You don't have to hard code all your checks. You just, like, the LLM can look at this and be like, maybe I can build, call a tool to turn this hex into actual ASCII code. So again, this is something you could build into an agent for deobfuscation. And then this is what I mentioned earlier. Can we social engineer the analyzer? So this is, again, that same piece of code. It's basically pulling a URL, and it turns out this URL is pointing to some malicious domain. Can you say, oh, I'm going to comment this as benign code that downloads benign functionality from a remote server, and then I'm going to say benign code has been executed, and I'm going to print it. And then see if an LLM is going to go here and try and classify this code. This is where prompt injection matters. You're like, okay, yeah. So this is basically from the movie Star Wars. It was like, yeah, there's nothing to see here. Does this work on an LLM? So that's an interesting exercise for you to try out. Here's another one. So when that simple ROT13 sort of way of hiding the function call, this is actual malware, and this is done at a much higher level. All of these package imports, they're actually importing functions into these basically crazy strings. And this is the kind of thing you could have an LLM undo pretty easily. These are the string substitutions. And so if you got this Python code, one of your first steps would be like, deobfuscate this for me. And then you reverse engineer it. Then you, in fact, you might have a deobfuscator agent. And then once that runs, you could pass it to the reverse engineering agent so that it actually has a better chance of giving you accurate information. So that's the idea here. This is the one I'm going to have you run. So look at this program. This used to be, this is a CTF challenge, actually. So you're like, yeah, the idea is that, do you know Python well enough to basically all of these characters are indexed from this one array. So this is brutal. You're going to have to write a program to deobfuscate this program. But then you're like, for the lazy people, you're like, can I just have the LLM do it? Turns out, yes. You can say, copy and paste this, and this is what you're going to do, and find what the flag is. So CTFs, you have to find the flag. That's basically what this is. The flag is there, and if you provide the flag, you'll actually get the provide the password correctly, you'll get the flag that will solve this level. So that's an interesting example. The next one, for those of you who like the CS205 CTF, so did you all take CS205 here? There's that CTF where we have you reverse engineer binaries. And this was before, like, that CTF was made long before LLMs were there. But you're like, oh, I do an object dump on this thing, and I'm expected to be able to read this assembly code to figure out the password that I need to enter in to get the good job to print, right? And this is the ASCII strcomp level. And so what it does is it compares the very first character that you have entered in with there's a character here somewhere. Well, it reads what your prompt is, and it compares a single character, the very first character, to a particular constant, and then it does a strcomp on the rest of it. So that's a level. So if I copy and paste this binary, I do an object dump, and I copy and paste this into the LLM, have I completely blown up the CS205 CTF? So don't tell anybody who's taking CS205 or who might be taking CS205. The answer is yeah, actually. You can just say, hey, LLM, do my CS205 CTF homework for me. And that's what you'll do. When I started this course, the answer was no. The LLM was too dumb. But now I just tried it over multiple ones. It'll actually do this. But the whole point of doing this is that this is really painful for an LLM to do. This is a whole bunch of tokens. Like binary is like, it's not a compact representation. It's like super large, like these binaries are large. What you would really want to do is basically send the level in its source form. So the LLM has been trained mostly on source code. It has not been trained on arbitrary binaries. I know of no foundation model that has been trained on a collection of binaries. Like nobody does that. So if you know the LLM is much better at seeing regular source code than binary code, then this will actually be more accurate because it understands code and use a lot less tokens because this C file is much smaller than that full-on binary in the previous slide. So this is where the engineering comes in. If you're trying to do automated binary analysis, what you want to do is send it to a disassembler first, or decompiler, and then use the decompiler output for the LLM. So that's basically what the last lab is. You're like, okay, so I'm trying to build a reverse engineering agent, an LLM agent, but I need to give the LLM some help. And so if you have a CTF binary that's in ELF, well, you could just send it into the Ghidra decompiler and then give the output to the LLM. Now, initially, when I started this exercise, this was the only way to do it. The LLMs would suck at the other ways. The LLM could do this very easily. The LLM couldn't do this. And then by doing the translation for the LLM, you give the LLM a little bit of help, it could definitely do this. But still, this approach is still valid because what you're doing is you're actually saving a whole bunch of inferencing on the LLM end. Like, because you're translating the problem into the domain that the LLM is good at. So that's the point of this exercise. So you're going to do it with Ghidra, you're going to do it with R2 and the R2 decompiler, and you're going to see that, yeah, if I translate this into a C domain, and then I have the LLM work on the C code, I'll get better results. It'll be cheaper. I don't have you measure the costs, but it'll be way less tokens, and it'll be more accurate, especially for more complex CTF levels. Okay, so those are all the exercises I'm going to have you do. So I'm just going to let you start with them. I finally updated all the labs, so I'm basically at a point now where I'm just finishing the labs right before I come to class now. I know people are working ahead, and I'm sorry if you got the older version of these labs, but now I think they're good. So people are sending me updates, and I'm like, oh yeah, that's because I'm not there yet. But I think I'm pretty good now. But if you have any bugs that you come across, yeah, let me know. All right.